With the brief introduction, we will also look at how the gross primary production is typically estimated for terrestrial ecosystems. It's different for marine ecosystems, but gross here means the net, the amount of carbon fixed. Net obviously means there is some that is respired by the plants themselves, so that is a loss, and this is just the total primary production, just like gross income and net income where you pay a tax and so on. Okay, so we basically define a simulation of CO2 during photosynthesis as A, where GS is the stomatal conductance. It's basically stomatas are trying to open, and nutrients and water vapor have been brought up to the leaf by the root system and the capillary action up into the tree, and they are opening the stomata to capture CO2, and the stomatal conductance basically is trying to optimize capturing enough CO2 not losing too much of the water vapor that is preciously brought up by the root system, right? So the Ca and Ci here are mole fraction of carbon CO2 outside or in the air and inside in the leaf. Okay, so this is stomatal conductance times the difference of the mole fractions of CO2 in the air and in the leaf. That's how much CO2 is assimilated and converted into carbohydrates. E here represents the transpiration. Okay, so that's the loss. D is the vapor pressure deficit. So saturation minus E. So E is the actual water vapor content of the air surrounding the leaf, and ES is the saturation water vapor pressure. So remember we talked about humidity and aridity indices. So when we look at the global warming responses of vegetation, it turns out that this water vapor deficit can become very critical. So it's not just the water vapor levels, but the difference between maximum water vapor that the air can hold at saturation and the water vapor that's actually available. Okay, so transpiration then is some factor 1.6, which arises because water diffuses through the stomata faster than CO2 can. Okay, that's just a physiological reality. And again, GS is the stomatal conductance, and D is this water vapor deficit. So gross primary production is obviously a combination of this transpiration and assimilation of carbon. So A over E then is Ca approximately equal to air mole fraction minus leaf mole fraction of CO2 divided by the water vapor deficit. The ratio of Ci over Ca ranges only between about 0.5 and 0.9. That's from empirical evidences. So A over E is approximately proportional to Ca over D. So it's the availability of carbon dioxide in the air and availability of water vapor. Okay, Es minus E. So E is the actual water vapor content in the air around the leaf where the stomata is opening. So if the stomata is opening and there is too little water vapor deficit is high, then the leaves tend to lose too much water. So then they close soon before enough CO2 is captured, let's say, in a simple sense. So that minimizes or that affects the amount of carbon that can be fixed. Okay? So GPP can be made on the assumption that it is proportional to the total water used by the ecosystem, which can either be measured as the difference between precipitation and runoff. Okay, so there is rain and then there is runoff, and the trees are modulating the runoff because the root system is controlling how much water gets taken up, or computed as a function of precipitation and atmospheric evaporative demand. Okay, how much water is being lost from the leaves, let's say. Okay, so the other way is to look at light use efficiency. So in this case, A is a function of the intrinsic quantum efficiency of photosynthesis. We won't say exactly what it is. I is the incident photosynthetically active radiation, and FA par is of course the fraction of absorbed par, and then Ci again is the mole fraction of CO2 below which no photosynthesis occurs. So unless CO2 is above a certain threshold, the plants are not going to spend the energy to try to photosynthesize. And gamma star here is the CO2 compensation point. Sorry, I said it wrong. Ci is the CO2 in the leaf, and gamma star is the CO2 compensation point, which is the minimum CO2 required to drive photosynthesis. Okay, so that's divided by Ci plus 2 omega star. Okay, so water use efficiency, which is what we looked at here, and light use efficiency respond to CO2 and can produce actually different GPP or gross primary productivity responses. Okay, so we have to be careful of how you use them. Okay, we will use that to see how we will estimate the response of or the impact of global warming on vegetation and ecosystems. So here you look at the last freeze day of the year. Obviously it's happening earlier and earlier, which means that the spring is arriving earlier, winter is ending very soon. So the winter months are here, and there is a large variability, but there is definitely a trend here. Okay, so this is year 1960 here and up to here 2010, and the first freeze day is arriving later and later. So this is 131 with some range, this is 279 plus some range. So essentially that means the number of freeze days have been squeezed. It's freezing later and later, and the last freeze day is arriving earlier and earlier. So the thaw is starting earlier, freezing is starting later, so the number of freeze days are decreasing. That's important because number of pests that get killed and so on gets affected severely by that as well. Okay, so this is the freeze period in days. So you can see that that's decreasing, but the growing season is increasing, right? If you have enough temperature, enough light, enough water, the growing season is going to happen. So the trend is 148 plus minus 0.37. So you can see that the average, sorry, you can see that the growing season is increasing as we talked before, and the freeze period is decreasing. So we have to then put that in the context of how global warming will affect trees and grasses. So again, C3 and C4 and CAM type plants. Mostly we worry about C3 and C4. So estimates of the past atmospheric CO2 levels have been made using models like this one by Berner, and there is very high CO2 in the atmosphere with this uncertainty range here during the time of the dinosaurs, which was a very warm period. In fact, it is known as the Cretaceous hothouse. When we talked about before, we mentioned that there was no Antarctic glaciers, Greenland glaciers, no Arctic sea ice, mammoths and all sorts of dinosaurs and so on were wandering around in the Arctic Circle. Vegetation was very different, and slowly over time CO2 has dropped. We are here to the current level of 400 now, and this is the oldest C4 plants, and then global increase in C4 plants. So remember that C4 plants do better in low CO2, so they evolved to take advantage of these changes over time period. So let me come back to the wildfires in the next podcast, but just keep track of these various parameters that are very critical for terrestrial ecosystems, because when we talk about feedbacks in the Earth system with global warming and human activities, and we want to see how future response of the terrestrial ecosystem is going to affect forests, food production, crop yields, etc. We need to have these simple backgrounds. So make sure you just have a very good sense of all these different variables that matter and that are already showing some trends in terms of growing degree days and number of freeze days and so on.